So section 1.7 is all about linear independence, and we're going to first look at this formal definition, and then we'll look at some more informal ideas around it. So the definition of linear independence, we have an indexed set, so in other words, just an ordered set of vectors. These vectors are in Rn, which means they have n components, is said to be linearly independent if this vector equation has only the trivial solution. So in other words, if all of the weights, the x1, x2, xp, are all 0. So the set is considered to be linearly dependent if there are some non-zero weights. And I don't mean that all of them have to be non-zero. I just mean at least one of them has to be non-zero. Equation 2 in the above definition is called linear dependence relation. So this is the linear dependence relation among the vectors v1 through vp when the weights c1 through cp are not all 0. Exercise 1 asks us to apply the definition above to show that these three vectors, 1, 0, 0, 0, 1, 0, and 0, 0, 1, is a linearly independent set. So it is linearly independent if there are weights, I'm going to call them C1, C2, C3. So we have weights, C1, C2, C3, and if C1, C2, C3 are all 0, then it's linearly independent. To solve this, I'm going to put it into an augmented matrix. Notice it's already row reduced, so we can see here that this row tells us that C3 is 0, this row tells us C2 is 0, and this top row tells me C1 is 0. So because C1, C2, C3 are all 0, this is a linearly independent set. So now I'm going to apply the same definition and show this is a linearly dependent set. So again, I'm trying to find weights C1, C2, C3. C1 times 1, 0, plus C2 times 0, 1, plus C3 times 1, 1 has to equal 0, 0. So when that equals 0, 0, the only possible solution would have to be C1 is 0, C2 is 0, C3 is 0. So putting this into an augmented matrix, right now I see that C3 is free. In other words, it can be anything. That tells me C3 does not have to be 0, so linearly dependent. Another way to think about that, just by observation, so looking at this set, if I notice that if I add the first two vectors together, I will get the third vector. So the third vector really depends on the first two, but just by observation. Theorem 7 says that if we have an index set of two or more vectors is linearly dependent if and only if at least one of the vectors in S is a linear combination of the others. For this exercise 3, how to construct a linearly dependent set. First, let's start with two vectors that are linearly independent. So I know those two are linearly independent because they are not multiples of each other. So if you just have two vectors, I can look easily to see if two vectors are dependent or independent. They are dependent if they are multiples of each other. So if I want to create a dependent set, I can take any linear combination. So I know these two are independent. So if I add them together, this fourth one is dependent on the first two, or it's a linear combination. So it's 1 times the first one plus 1 times the second one. So the fourth one is a linear combination of the first two, so this is a dependent set. So just some special cases. I already kind of mentioned this first one. If you have two vectors, they are linearly independent if and only if they are not scalars of each other. If you have a set of three vectors, u, v, and w in R3, and the first two are independent, the set UVW be linearly dependent if and only if W is in the plane spanned by U and B. This first picture is trying to show that W is in the plane, that light blue area, defined by the span of U and V. And the second picture is showing that the vector W is not in the span of U and V. Theorem 8 says that if a set contains more vectors than there are entries in the vector, then the set is linearly dependent. So in other words, if you have 4 vectors in R3, 4 vectors that are all in R3 will be dependent. Theorem 9 says that if we have a set of vectors in Rn and it contains a 0 vector, then it's automatically linearly dependent. All right, so we're going to classify all these sets as either linearly independent or linearly dependent. Again, doing as little calculations as possible. So notice I can get from one vector to the other by multiplying by -2. So because they are multiples of each other, these are linearly dependent. There is no multiple that will get from the first vector to the second vector, so these are linearly independent. This one contains the 0 vector, so it's linearly dependent. This is 3 vectors in R2, so more vectors than the dimension, so these are linearly dependent. There is no multiple to get from here to here, so they're not multiples of each other, so linearly independent. This is 4 vectors in R3, so these are linearly dependent. There is a multiple from here. I can multiply by -8, so these are linearly dependent. For F, this is, you can't really tell just by looking at it. This is linearly dependent, and we will look at an example more systematically in the next one. So if it wasn't easy to observe whether a set of vectors is linearly independent or linearly dependent, then we need to apply that definition. So we have 3 vectors, v1, v2, and v3. We want to know, are they linearly independent or not? So we want to know, are their weights C1 plus C2 plus C3? So when we solve this, do we get C1, C2, C3 equal to 0, or are there some non-zero values? So we know to solve this, we put it into a matrix and augment it. So when we row reduce this, we get this system, and it tells me that X3 is free. So this is because X3, or maybe I should say C3 is free. V1, V2, V3 is linearly dependent. So then it says, if possible, find a linear dependence relationship. All right, so I'm going to go ahead and solve, because I want to find what are the values of C1, C2, C3 that will give this dependence relationship. All right, so I have C3 is free, C2 equals 2C3, and C1 equals -5 C3. Again, that comes from looking at the first 2 rows of the matrix. So a generic form would be my C3 is free, my C1 is -5 C3, and my C2 is 2 C3. Let's pick C3 equal to 1. So I would get -5 to 1. So what that tells me is -5 times my first vector plus 2 times my second vector plus the 1 times my third vector equals 0, 0, 0. So this tells me my linear dependence relationship among the three. All right, so another important piece of information. The columns of A are linearly independent if and only if AX equals 0 has only the trivial solution. So just to remind you, this if and only if means an arrow both ways. So it's basically saying if you know the columns are independent, then you know AX equals 0 has only the trivial solution. It also tells you that if AX equals 0 has only the trivial solution, then the columns of A are linearly independent. So if you know one side, you know the other side. So I want to determine in example 6 if the columns of the matrix A form a linearly independent set. So according to this theorem, the columns are independent if AX equals 0 has only the trivial solution. So I can augment A with 0 and row reduce. When I look at the row reduced matrix, if I call these x1, x2, and x3, I can see that x3 is 0, x2 is 0, and x1 is 0. So that tells me, because all my weights, my x1, x2, x3, are all 0, that is linearly independent. So now looking at the connection between linearly independence and span. Again, span is a linear combination of vectors. So this theorem says that a set of vectors is linearly dependent if and only if, again, both directions, one of the vectors is in the span of the others. So if I know my set is dependent, I know that one is a linear combination of the others. Also know that if I have a set and I know that one is in the span of the others, that it's dependent. So kind of a visual representation is that, this W is in the span of the other two. So I know that W depends on U and V, or it's in the span of U and V. That makes the set that contains U, V, and W dependent. All right, I want to know in this question, for what values of H is V3 in the span of V1, V2? Sorry, what does it mean for V3 to be in the span? So V3 is in span of V1, V2 if V3 equals some constant times V1 plus some constant times V2. In an augmented system, I'm for my V1 first, and then my right-hand side is the V3, so 5, negative 7, H. If I row reduce this, I will get 1, negative 3, H, and then 0, 0, 8, and then 0, 0, H minus 10. This second row tells me that 0 equals 8, so no solution, which tells me that V3 is not in the span of V1 and V2. Part B wants to know for what values of H is V1, V2, V3 linearly dependent. All right, so we're going to make some observations that you may have already noticed. To get from V1 to V2, you multiply by negative 3. That tells me the set V1, V2 is linearly dependent. So if I add another vector in there, it doesn't matter what that vector is. It'll still be linearly dependent because V1 and V2 are dependent. So H can be anything. I would recommend, when thinking about things being linearly independent or not, to really take a few seconds and just see if you can see a linearly dependent relation. Like, are there any multiples? Can you add any together to get a third? So it's worthwhile to just make some observations first before diving into the matrix operations.